Hello, I'm Sai. I am here to discuss the science project. The reports of both the phases have been enclosed here. This is the phase 1 report. Now the aim of the phase 2 is to understand and verify the Zelinsky equality using the calculations of potential of mean force PMF for the trajectories obtained using steered molecular dynamics SMD. Simulations need to be done on assigned protein. The protein assigned to me is 3JTC underscore C dot PDB. Zelinsky equality. The Zelinsky equality JE is an equation in statistical mechanics that relates free energy differences between two states and the irreducible work along an ensemble of trajectories joining the same states. It is named after the physicist Christopher Zelinsky. In thermodynamics, the free energy delta F, which is the difference between the states A and B, is connected to the work done on the system through the following inequality: delta F less than or equal to W, with equality holding only in the case of quasi-static process, that is when one takes the system from A to B infinitely slowly. The equality is derived from the other theorem called Crookes fluctuation theorem, which is an equation in statistical mechanics that relates to the work done on a system during a non-equilibrium transformation to the free energy difference between the final and initial state of transformation, and the equality is as follows: e power minus delta f by kt equal to e power minus w by kt. E power minus w by kt is the average work done over all trajectories. The equality is given by the above equation. For reversible process, the equality holds, otherwise right hand side value will be larger than the left hand side value. Upon simplifying, we can write the above equation as f of c of t minus f of c of 0 equal to minus t log x of minus w of t by t, where t is the temperature. After expanding RHS, the following equation is as below. The term RHS are called cumulants. The PMF estimation is done using three different forms. The first is the exact equation, the second is the first order cumulant, and the third is the second order cumulant. The script used to do PMF estimation is cumulants.tcl. Finally, all those three estimates are plotted in the same graph. Now, the procedure I followed is new trajectories are created by setting velocity to 0.00002 angstroms per time step in smd.tcl file. In smd.namd file, I took time step as 0.5 frames per second step and ran 10 power 6 times. Each trajectory is present in d underscore smd underscore tcl.out file. Ran the command dot slash namd to smd.namd and redirected the output to da underscore smd.log, and the log file contains 20,001 lines. Then copied the log to trajectory1.out file and ran the above command two more times and stored the results in the trajectory2.out and trajectory3.out files. For making da.dat, the files were combined using Excel, and a tab delimited .dat file was made the first column as time, second to fifth as trajectory distances, and 6 to 8 column as force applied. The code is present in makedata.py file. That for loading the trajectory into VMD load trajectory.tcl script was used, and the numbers range from 1 to 20,001. The script has three variables: t, which denotes time steps, 20,001 rows; z is a 20,001 cross 3 matrix which contains end-to-end distance; f 20,001 cross 3 matrix which contains force trajectories. First plot was made using plot extension time.tcl with time on x-axis and extension on y-axis. Here we first atom in TCL file fixed and last atom is pulled with same force and velocity. Values are same as that of used in phase 1. Here is the plot for extension versus time. Now second plot was made using force extension.tcl, which as plot for force against extension. For work calculation, we run following commands in tk console of VMD. Set time step to 0.1, set v t c, which is an array to be declared to store distance between constraint points, and set I, which is the initial constraint distance, as below. Now we run the while loop and keep update I using Newton's equation of motion. Distance is equal to initial position plus velocity into time. Work is calculated using script calc2.tcl and plot is made using plotw.tcl. The plot is as below. The work done y is on y-axis and extension is on x-axis, and this is run for three simulations. As defined above, we use the Zelinsky equality here. From last equation, we can calculate the change in work done using the left hand expression. Run source cumulants.tcl. This gives f exponential that is equal to minus t log w of t by t, f of 1 equal to average work done, f of 2 equal to 1 by 2t average of w of t square minus average of w whole square. We plot this f1, f2 and fx by the following commands. We plot the f1 in green and f2 in blue and fx in black. The graphs are as below. Now the three molecules taken for comparison are 1 mine, 2 Kaushik's and 3 Avinash. The first plot is extensions versus time plot. Time on x-axis, extension on y-axis. This is mine, this is Avinash and this is Kaushik's graph. The graph is varying linearly for extension versus time plot. Force versus extension plot. Graph fluctuates but varies linearly almost extension on x-axis and force on y-axis. This is my graph, this is Kaushik's and Avinash graph. The third graph is work versus extension plot. Graph varies exponentially here, extension on x-axis and work on y-axis. The dissimilarity in the graph is due to the zoom sensitivity and the difference in the molecules. The PMF decreases exponentially for F2, whereas for F1 and Fx it increases almost linearly, which can be seen here. This is my graph, this is Avinash and this is Kaushik graph as it can be seen and the variations are observed. The inference. Change in free energy is same regardless of the path, but it is equal to work done if it is quasi-static. If we want to change the free energy, we need to use Zelinsky equality. The three curves are different approximations of Zelinsky equality. The files can be referenced in the Google Drive link kept below.